Okay, question 6. We have a cylindrical shell. Okay. Its radius is 7 centimeters. Okay, we can get rid of that 7 centimeters right away, change that into meters, 0.07 meters. Okay. It's important to note it is a shell, so it's hollow. It has a length of 2.4 meters. It has a charge that is uniformly distributed on the curved surface. Okay, so on the surface of this cylinder, there is a charge. The magnitude of the electric field at a point 19 centimeters radially outward from the axis, so 0.19, we'll have a larger sphere, or a larger cylinder, sorry, going over this. The electric field that we feel here, radially outward, measured from the midpoint, is 36,000 newtons per coulomb. It says 36 kilonewtons per coulomb, so 36,000 newtons per coulomb. Part A, find the net charge on the shell. Okay, so this is a Gauss. We're going to have to use Gauss's law, which means our flux is equal to E dot dA, or Q enclosed over epsilon naught. Okay, so this one told us a little bit of something different. It didn't mention flux in there in any ways, but it did tell us there was a charge. That's what we're actually looking for. Find the net charge on the shell. We want to find Q. And it told us what the electric field was. Okay, so we'll start plugging in. The electric field is uniform because it's a circle, a cylinder inside of a cylinder, so the electric field is constant. We can pull that outside of the integral, and then we can just integrate the area for the total area of our shell. Okay, so let's start off with E times the area would be equal to the Q enclosed over epsilon naught. Well, now E was given 36,000. The area, the surface area of our shell, okay, is going to have to be what? Well, it'll be the shell that we made. Okay, the outside one here, the one that we made at 19, because that's where we're getting our electric field from, so that number better correspond with it. So the area would be its circumference times its length. Okay, circumference of this would be 2 pi r. R in this case, 0.19. So that's the circumference multiplied by the length. The length, let's make it the same length as that. Let's make it 2.4. Okay, so you could also have E times 2 pi RL if you want to use, if you don't want to plug in numbers yet, that's fine. 2 pi RL. This is equal to the Q in over 8.85 times 10 to the negative 12th, epsilon naught. Now we've got just straight up numbers. Multiply all these numbers by 8.85 times 10 to the negative 12th and solve for the Q that's enclosed. Everything looks positive. So the Q that you get from this should be 9.13 times 10 to the negative 7 coulombs. Okay, that's how we get the number up here. Part B. Find the electric field at a point 4 centimeters away from the axis, measured radially outward from the midpoint of the shell. Okay, so now we're going inside the shell. And we'll have another cylinder inside. Okay, so this is part A. Part B. So we'll have the same thing. We'll have an E dot dA, Q enclosed over epsilon naught. The electric field there I don't know, but I know what the charge is. Okay. We could pull the E out if we wanted. We could have E times our area. Our area, again, is going to be 2 pi. This new radius, 0.04 times its length, 2.4, okay, equals to the amount of charge that's enclosed. How much charge is enclosed inside of that spheric or of that cylindrical shell? Well, none. 0. Reason it's 0 is it says right in the problem that it has a charge uniformly distributed on its curved surface. Okay, it is a hollow cylindrical shell. There is nothing inside. There's just air in here. So there's no charge that's enclosed. If there's no charge enclosed, this whole side becomes 0. That means that our electric field over on this side is 0. And that's how you get electric field of 0.